Welcome to the wonderful world of physics. We're in the unit on thermodynamics, chapter 17, the thermal behavior of matter. In this video, we're going to look at section 17.2, phase changes. Before we do, I'd like to do a quick review of a concept in section 17.1, the previous video. I'd like to look at problem number 36. It says a helium balloon occupies 8 liters at 20 degrees Celsius and 1 atmosphere pressure. The balloon rises to an altitude where the pressure is 0.65 atmospheres and the temperature is negative 10 degrees Celsius. What is its volume when it reaches equilibrium at the new altitude? So this is a good example of the very useful equation PV equals nRT. First, I've written out the given information, as I always do when I begin problems. The original volume is 8 liters, temperature is 20 degrees Celsius. We need that in Kelvin, so let's add 273.15 and get 293.15 Kelvin. And the original pressure, P naught, is 1 atmosphere. Over on the right, I've written that P1 is 0.65 atmospheres. The temperature is negative 10 degrees Celsius. Let's call that 263.15 Kelvin. And we want to know what V1, the new volume, is. So let's use PV equals nRT, and we'll use a very useful technique where when quantities are changing, we're going to algebraically put all the changing quantities to the left and put all the constant quantities to the right. So PV and T are all changing. We'll take PV equals nRT, divide both sides of the equation by T. So PV over T, the changing quantities are on the left, equals nR is constant. And now we have this relationship that PV over T equals constant. And we don't care what that constant is. We don't care what N times R is. What is important is that PV over T, those three quantities in that relationship, will remain constant. So then we say P1 V1 over T1 equals P naught V naught over T naught. So the PV over T of the new situation equals the PV over T of the original situation. We want to know what V1 is, so let's solve that algebraically for V1. V1 is, and you see that it's related to the original volume. It's related to the ratio of the pressures, P naught over P1, and it's related to the ratio of the temperatures. The ratio of the temperatures, T1 over T naught. We plug those values in. We can keep volume in liters. We can keep the pressures in atmospheres because whatever those units are, as long as they're the same, they're going to divide out. And we're left with 11.05 liters, or we'll round that to 11 liters. Now let's move on to section 17.2 on phase changes. Phase changes are a material going between the phases of solid, liquid, and gas. You look at the picture down below, and here is a solid array of molecules. A solid means that the molecules are tightly bound together in an organized array. And these phases have to do with the molecules being bound together. So in a solid, they're bound together in a certain structure. And a solid has a fixed volume. It has a relatively fixed shape. But then above that in the picture, you see a liquid. Now, a liquid involves the molecules, and they are very loosely bound to each other. They don't have the rigid structure of binding that the solid does, but they have loose, sometimes very temporary bonds with each other. So when we go from solid to liquid, we call that melting. And when we go from liquid to solid, we call that freezing. Now with a liquid, the molecules are free to move around, but they're loosely bonded to each other. If you add more heat to it or add more internal energy, then those bonds will completely break apart and the molecules will not be bonded to each other at all. And that's called evaporating or evaporation. So going from liquid to gas. If it's done more rapidly, we might refer to it in everyday language as boiling. It goes from liquid to gas. And you can see up at the top, the gas, it doesn't have any fixed volume or fixed shape. It will fill the container that it's in. Going from gas to liquid is called condensing or condensating. So generally as something gets hotter, it melts from solid to liquid, and then it might evaporate from liquid to gas. If it gets colder, it'll condense from gas to liquid, and it'll freeze from liquid to solid. It's important to note this second bullet comment, or let's go up to the first one actually, that heat is required to break those molecular bonds. We input energy into the system, and that's what breaks the bonds. The second bullet point, important to note, is that while the bonds are breaking, there is no change in temperature. So if you have ice and you are putting heat into it, while the ice is melting, all of the energy is getting devoted to breaking those bonds, to changing it from solid to liquid. The temperature will not go up until it's liquid. Here is the equation that relates how much heat we put in versus how much is going to melt. It's Q equals ml. Now Q is the amount of heat that we put in to the substance. The mass is its mass. And I put there an L. Now sometimes it'll be L with a subscript F and sometimes with a subscript V. So there are two different L's for every substance. The heat of fusion, L sub F, is the heat required to break it from solid to liquid. We call that the heat of fusion. By the way, if you're wondering why the letter L, because it's actually called the latent heat of fusion and the latent heat of vaporization. So, but we'll just call that the heat of fusion, heat of vaporization. L sub V, the heat of vaporization, is the heat required to turn something from liquid to gas. The equation at the top left of the screen works in both situations. You just use different constants. You look at table 17.1, which will be useful for the various examples and homework problems that we'll do. And let's just look at the first one, alcohol, ethyl alcohol. It gives the melting point, 159 Kelvin. The heat of fusion is 109 kilojoules per kilogram. What that means is if you are going to melt it from a solid to liquid, for every kilogram of mass, you need to input 109 kilojoules or 109,000 joules. The boiling point is 351 Kelvin. The heat of vaporization is 879. So if you're going to boil it, assuming it's already at its boiling point of 351 Kelvin, you want to boil away that 1 kilogram, you need to put in 879 kilojoules or 879,000 joules of heat. You'll notice if you look in the third column and the fifth column for this variety of substances, you have the heat of fusion, which is the heat per kilogram that it takes to melt it. And over in the fifth column, the heat of vaporization, the heat required for every kilogram to boil it. You'll notice in every one of those situations, it is substantially more heat to boil it than to melt it. So heat of vaporization is going to be greater than the heat of fusion. It takes a lot of energy to melt something, but it takes a lot more energy to boil something. Well, if you look down at the bottom of the chart, one that we'll be using frequently because it just comes up a lot in practical application is water. And so water is in the table in the third column, it says the heat of fusion. So the heat to melt it is 334 kilojoules per kilogram, but most likely in our calculations, we'll be needing joules for those MKS units. So 334 times 10 to the third joules per kilogram, which by the way is 80 calories per gram. The heat of vaporization of water is 2257 kilojoules. So 2257 times 10 to the third joules to boil every kilogram of water. And again, that assumes it's already at the boiling point. So in this discussion, we're not even talking about raising its temperature to get it up to boiling point. This is simply to boil it. Let's look at this conceptual example from the book, example 17.1, water phases. It says you put a block of ice initially at -20 degrees Celsius in a pan on a hot stove with a constant power output and heat it until it is melted, boiled, and evaporated. make a sketch of temperature versus time for this experiment. So we start here. We can think of this, it's drawn it as the time arrow. The horizontal axis is time. But since it's a constant power output, the same number of joules per second, you can also think of that horizontal axis as not time, but heat, how much heat cumulatively we have put in. But here it's drawn as the time axis. It starts with a temperature -20, and based on the equation mc delta T, the amount of heat, which, remember, we have a constant power source, so you can think of this as how much time has gone by, is equal to the mass times the specific heat of of ice, times the change in temperature. So in the linear fashion, it goes up, 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 till it gets to 0. Now I want you to see, even though we continue to put heat into this ice, its temperature is not going to go up. While it's melting, it stays at 0 degrees Celsius. We keep on putting in heat, and intuitively we might think that its temperature should be going up, but no, the heat is being devoted to melting, to breaking those bonds between the water molecules. So it spends a significant amount of time melting. In fact, notice the amount of time as opposed to the amount of time that it took just to raise the temperature. It takes a significantly more amount of time because it takes a lot of energy to melt ice. And then once it gets all melted, now it's water. Now, based on Q equals mc delta T, it goes up, the temperature goes up 40, 60, 80, and it gets up to the boiling point, 100 degrees Celsius. And notice it does not go up to 105, 110, 115, 120. It doesn't do that because now all the heat that previously was put into raising the temperature, now that it's up to 100 degrees, now all the heat is going to get invested into boiling the water away. And it's not going to go above 100 degrees until it's no longer a liquid. So once it's a gas, it will then go above 100 degrees. Now, practically speaking, in this problem, I imagine that we're doing this in a kitchen. And in a kitchen, that gas isn't going to go above 100 because it's going to escape into the air. It's going to make a bit more humid the kitchen and the house. But that's kind of where it ends. But if we could do this in a closed container, a closed system where we're capturing all that boiled water, all that vapor, then yes, you keep heating it and it will go above 100, but that's only way down the line. They've drawn this little break right here to show it actually extends probably beyond what the page allows. During the phase changes, the temperature is constant. And eventually, way down here, probably off the page, eventually, once it's all gas, there's no more liquid water, then the temperature will go up. The got it question at the bottom says, you bring a pot of water to boil and then forget about it. 10 minutes later, you come back to the kitchen to find the water still boiling. Is its temperature A, less than, B, greater than, or C, equal to 100 degrees Celsius? And the answer is, if it's boiling, if it's in the process of boiling, it's equal to 100 degrees Celsius. Now, this is an important practical point for home economics, for cooking in the kitchen. Very often, recipes, when cooking instructions, they say, bring it to a boil, bring the pot of water to a boil, and then bring it down to a simmer. And so the reason you bring it down to a simmer, so when you're boiling the water, you probably have that dial up to 10. You have the stove on full. But once the bubbles start coming, those rapid bubbles, you can reduce the stove down to low, down to maybe 1 or 2 out of 10. And as long as the bubbles keep coming, it's 100-degree water. That's what the recipe, whatever you're cooking, that's what it requires. 100 degrees Celsius water, or 212 degrees Fahrenheit. And so whether your stove is putting out a lot of heat, you've got it cranked up to 10, or putting out a little heat, you've got it cranked down to 2. As long as those bubbles are coming, you've got 100 degrees Celsius water. So you can save energy, and probably save maybe some boiling over, some spilling over, making a mess, if you turn down the heat and just give enough heat to keep it boiling. Let's look at problem number 19 in the back of the book. Pretty simple problem. It says it takes 200 joules to melt an 8-gram sample of one of these substances. What is the substance? Okay, so first we're going to focus on that it's talking about melting. So we're going to look over here at the heat of fusion. We're going to ignore heat of vaporization because that regards boiling. We're going to look at melting. And the question is asking, what is the substance? Meaning, when we put together that 200 joules of heat, the 8 grams mass, we should be able to come up with what is the heat of fusion. And from there, look at the table and see which one matches most closely. So I write down the given information. Mass is, it said 8 grams, but I need that in kilograms, so 0.0080 kilograms. It says a heat of 200 joules. I need the equation that Q equals M L sub F. And I'm going to solve that for L sub F, the heat of fusion. Heat of fusion for this particular experiment is the heat we put in divided by the mass, 200 joules over 0.0080 kilograms, and that gives me 25,000 joules per kilogram. Now 25,000 way exceeds any of the numbers on that chart, and then we remember that's joules per kilogram. The chart gives it in kilojoules, so 25 kilojoules per kilogram. And we look on the chart to see which one is, or at least is close to 25 kilojoules, and we see, yes, right here, lead, 24.7. So of these substances, that's the answer. I want to now do an example that puts together concepts learned in the previous section when we talked about, or a previous section, we talked about the raising of the temperature of an object. And now we're talking about phase changes, and we're going to put it all together. So let's say we start with 900 grams of ice that's at a temperature of negative 20 degrees Celsius. How much heat is required to boil it all? So it's ice. We want to boil it away. It's going to take a lot of heat. Here's what we're going to do. We need to think about this substance. We need to think about all the different steps it's going to go through to get from the beginning to the end. So the beginning is that it's ice at negative 20 degrees Celsius. So let's think, what processes have to take place? We're going to list them out in order. And the first step is this step 1. It is ice, and it starts at negative 20 degrees Celsius. And first, step 1, I'm going to write it out like this. Ice needs to be brought from negative 20 degrees Celsius to 0 degrees Celsius. Now, I'm not going to bring it to 100 degrees Celsius, only to 0, because that's the first step. The next step is going to be that it melts. So let's just take it up to its melting point and stop there for step 1. Once it's 0 degrees Celsius, it's going to melt. That's step 2. Once it melts, it's now liquid water. So step 3, as we continue to put heat into it, its temperature goes up from 0 all the way up to the boiling point. So we're going to stop that at 100 degrees Celsius. And then the third question says that is the third step. The question says we're going to boil it all. So all of that water we're now going to boil. So we've got these 4 steps in chronological order that it's going to take. Here's the necessary information that's relevant to these steps. When we're raising its temperature, we need the specific heat of ice, 2050 joules per kilogram Kelvin. When it melts, we need the heat of fusion. When it's water that's having its temperature raised, we need the specific heat of water. And finally, when it boils, we need the heat of vaporization of water. So those are the 4 relevant quantities. If we want to know how much heat, we're going to add the heat from each step. So the amount of heat is Q1 plus Q2 plus Q3 plus Q4. And then I'm going to break down each of those Qs and see what does each one involve. Well, Q1, since it's a raising of a temperature, is MC delta T, and that refers to ice. So make sure you have C sub I. And I say delta T1 meaning the change in temperature for step 1, plus MLF for melting it, plus now it's water, MCW delta T3. Make sure you have the specific heat of water, which is different from the specific heat for ice that we used in step 1, and times the change in temperature for step 3. And finally, to boil it, mass times heat of vaporization. I've used the same M because it's not changing, so one of the things I can do if I want to is factor out the M to the left so I don't have to type it into the calculator 4 times. Now for this example, I did not factor out M because I'm curious later to see how much heat went into each step. So there we have at the top of the screen where we left off with on the previous page. Now we're going to plug in all the values. So we have the mass in kilograms, we have the specific heat of ice times, while it was in that first step just being ice, it went up 20 Celsius degrees. We have mass times heat of fusion, plus now we're going to raise the temperature of the water, so we need the specific heat of water, 4184, times it went up by 100 Celsius degrees in that step, plus mass times heat of vaporization. I've calculated each of those, and you notice only 1% of the total heat, it rounds to 1%, went into raising the temperature of the ice. About 11% went into melting the ice. About 14% went into raising the temperature of the water. And the majority of the heat went into simply boiling the water, turning it from a liquid to a gas. So we add all those up and we get a total of 2,745,000 joules. And then I want to know, what if we have a constant power, a constant heat source, a 1600 watt heater? How much time is this going to take? So if power equals Q over T, then T is Q over P, or heat over power. So we take the amount of heat, 2.7 million joules, divide by 1600 watts, or joules per second, and we get 1716 seconds, or about 29 minutes. So a significant amount of time, a significant amount of heat to take this ice, melt it, raise its temperature, and boil it all away. Now, that has been raising the temperature and boiling a substance. Well, first melting and then boiling. If we want to go in the opposite direction, cooling a substance, condensing it from a gas to a liquid, or freezing it from a liquid to gas, then we have to make Q negative. When we changed the temperature simply in a previous section, and we used Q equals mc delta T, the negative sign took care of itself. When delta T, if it was positive, the whole term was positive. If it was negative, the heat came out negative because you were doing final minus initial temperature. Here we have to arbitrarily add in a negative sign if we are, again, if we are freezing or condensing from a solid to a liquid, or a liquid to a, if we are condensing from a gas to a liquid, or if we're freezing from a liquid to a solid, we need to show that Q is negative because we're not putting in heat, we are extracting heat. And the math works the same, but you have to make Q negative to show that we're extracting the heat. So in this example, to turn 900 grams of water vapor to liquid, heat must be removed. So in that case, we're going to say Q equals negative MLV. And there you see I've put in the values, and we get 2 million joules, but it's negative, meaning the heat is extracted. Now, let's say we lower its temperature to 0 degrees Celsius. So we're taking it from the boiling point down to 0 degrees Celsius. And you can see Q equals mc delta T. We're dealing with water, so it's 4184 joules per kilogram Kelvin. Final minus initial, 0 minus 100 is negative 100. And that heat comes out negative 376,560 joules. I want to now look at phase diagrams. This is a diagram of where a substance exists, and by where I mean what pressures and temperatures it exists as solid, liquid, and gas. This particular phase diagram you're looking at is for water. Now I want you to notice we've got our vertical axis is pressure in atmospheres. So right here where the pointer is 1 atmosphere, right there. That's where you live, 1 atmosphere, sea level on Earth. But it goes down very low to 0 and it goes up high. This is not a linear scale as it's drawn. It goes up very high to 218 atmospheres, very high pressure where something interesting happens. The temperature on the horizontal axis, we start at 0 Kelvin, and we have right here 100 degrees Celsius, that's boiling point of water. And here is 0 degrees Celsius, freezing point of water, and you live somewhere around at this temperature. So we live approximately, this is about standard temperature and pressure, right about where my pointer is, right there. But you can see the temperature goes up on the scale to 374. Now, we tend to think of phases only one dimension on this graph because we tend to only think of one pressure wherever we live. So we live around sea level here in Porterville, so 1 atmosphere. And you know that water is a solid until about 0 degrees Celsius. Then it's a liquid, it melts and it's a liquid. We raise the temperature and then it boils, it's a gas. But now what I want to show you is that it does different things with different pressures and different temperatures. So as pressure increases, the boiling temperature of the water rises gradually from 100 degrees Celsius all the way up to 374 degrees Celsius. So as pressure increases, it takes more to boil that water. As pressure decreases, going down from 1 atmosphere, then boiling point gets lower and lower. And I'll talk about that referring to the chart down below in a minute. So this idea that the pressure, as pressure increases, the boiling temperature of water rises, this can be demonstrated in a pressure cooker, which cooks food faster than an open pot, because the water can exist as a liquid at temperatures greater than 100 degrees Celsius without it all boiling away. So it's pretty neat. With a pressure cooker, greater pressure, then the liquid water has a higher temperature than 100 degrees, and so the food will cook faster. Now this boiling curve ends at a certain point. You notice it just doesn't go off the chart. It ends right here. Now, so this curve right here, the separation between liquid and gas, it just comes to a stop. That's what's called the critical point. Notice it's a very high pressure. It's a pretty high temperature. Above this temperature, the liquid and gas phases cannot be distinguished, and the substance is called a supercritical fluid. So right in here, it's not liquid, it's not gas, it's kind of a hybrid in between. It's called a supercritical fluid. Now, at a sufficiently high pressure above the critical point, a gas has the density of a liquid, but it does not condense. And the pressure at this critical point is known as the critical pressure. Now, we've also got the triple point of the substance. For water, the triple point occurs at just a tad above 0 degrees Celsius. It's actually 0.01 degrees Celsius, and a very, very low pressure, that 0.006 atmospheres, which is about 611.2 pascals. And the triple point is the pressure and temperature where all three can exist simultaneously, liquid, solid, and gas. It's where they all come together. Now, I mentioned when I was talking about a pressure cooker that if you increase the pressure, boiling point goes up. Well, if you decrease the pressure, boiling point goes down. This is very practical application. If you go up to higher elevations, you go to higher elevations on Earth, go up into the mountains, for example, and boiling point of water, boiling temperature goes down. For each 500 feet increase in elevation, water's boiling point drops by approximately 1 Fahrenheit degree. And so at sea level, the boiling point of water, 100 degrees Celsius or 212 degrees Fahrenheit. But if you go up to a lot of towns in, for example, Colorado and Wyoming around the Rocky Mountains, 7,500 feet is a elevation where a lot of people live. The boiling point of water is only 198 degrees Fahrenheit. Well, what this means practically is that for cooking, when you are cooking your boiling water, you can only get water up to 198 degrees Fahrenheit. It will not go past 200. It certainly will not go up to 212 because at 198 it boils away. And it won't go past 198 until it's all gas and it's gone. So if you're cooking, you're boiling something, the food that you have in the boiling water is not being given a hot enough temperature. So you need to add a few minutes to the time that you boil it. For example, when I make hard-boiled eggs at sea level, by my own preference, I boil them for 12 minutes. But when I'm in Colorado, Wyoming, an elevation of between 7,000 feet, I know that I need to keep the eggs in a little longer because they're not subjected to as hot water as I can give them down here at sea level. So I tend to cook them instead of for 12 minutes, I tend to do about 15 or 16 minutes. If you go high up into the mountains, such as 13,000 feet, you go camping and you want to boil something or maybe just have some hot coffee, the temperature that water boils is much lower, 187 degrees Fahrenheit. So if you're making hard-boiled eggs, I don't know, I've never made hard-boiled eggs that high elevation, but it might take 30, 40 minutes. If you go to the highest mountain on Earth, which is about 29,000 feet, Mount Everest, the boiling point of water is reduced down to 158 degrees Fahrenheit. Finally, there's this interesting substance called dry ice. It is carbon dioxide in the form we generally have it. It's frozen. It's solid carbon dioxide. And this is its phase diagram. And you can see it looks similar shape as water had with the triple point, the critical point. There's the pressure. But what I want you to see, and what makes this such a fascinating substance, is that right here where its triple point is, where it can be solid, liquid, or gas, that's at 5.11 atmospheres. Now we live at 1 atmosphere, which is down here on the graph. So we have solid carbon dioxide, and you heat it up, you heat it up, you heat it up, and look what happens here. It doesn't become a liquid. It goes straight from solid to gas, and that process is called sublimation. It sublimates straight from solid to gas. And so that is what dry ice is. Now, if you do have higher pressures, such as above 5.11 atmospheres, you can have liquid carbon dioxide. But where we live at 1 atmosphere, it goes straight from solid and sublimates into gas. That is the end of section 17.2, phase changes. Have a great day.